In this section, we're going to talk about series. Now, in the previous section, we talked about sequences, right? So taking basically a list of numbers, and we were mainly concerned with whether that sequence converged or diverged, right? So sequences, here's our basic notation for sequences, right? A series is going to be taking the elements of that sequence and adding them together, all right? So while this sequence here was A1, comma, A2, comma, A3, dot, 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 this one's going to be A1 plus A2 plus A3 and so on. All right. Now, notationally, we're going to use this capital Greek letter sigma to indicate when we are summing things or making a series. And like the sequence, we'll tell it where we're starting and where we're going to. So if it's an infinite series, we'll say it goes from some starting point, often 1, up to infinity. Just like sequences, remember sometimes with sequences we would use lazier notation and just say, here's my sequence, and you don't bother writing the n equals 1 to infinity. You'll see that as well with series. So if it's left blank, you can assume that what's going on there is you're saying n equals 1 up to infinity. All right, so like we said, one of the things we talked about with sequences is whether it converged or diverged to a particular number. We're going to be interested in the same thing with series. Okay, so can I sum up infinitely many terms and have those terms add to some finite number, right? So in order to answer that question, it may be nice to be able to put things in a language that we're already comfortable with, right? So that's a good general principle to always go back to, right? When you're doing something new, is it like something old that we've done? Well, we just finished studying sequences, so the proposal here is that we think about turning a series into a sequence, and that's actually pretty easy to do. So what we're going to do is we're going to think about what are called partial sums. Okay, so here's the definition. The nth partial sum of this series is where you sum from 1 up to some number n, okay, and add up only those and then stop after that. So if I did S3, it's literally the first term plus the second term plus the third term, and then I stop. But what this does is it allows us to talk about a single number, right? And then I could do S4 and S5. And so what that does is the partial sums become their own sequence. And the reason that that's nice is because we know how to determine if a sequence is convergent or divergent, right? We look at the limit, right? Does the limit exist or does it not exist? So when we say a series is convergent, what we mean is that the limit of its partial sums as n goes to infinity exists, right? And is some number s. And we call that number s the sum of the series. Okay, it's what the series actually adds up to. And so we use often just this notation, say the series equals s, because it sums to it. All right, but we also saw plenty of cases in the previous section where the sequence diverged, right? The limit did not exist, and so if that's the case, then that means that our series is divergent. All right, so this is a lot of notation and vocabulary here, so let's do a concrete example to help us wrap our heads around this. So here's our series, and we want to ultimately be able to say, is it convergent or divergent? What does it sum? Answer all those questions. But first, let's make sure we have a handle on this notation. All right. So we're looking at the partial sums here. So first of all, S1. Okay, what does that mean? That means I'm taking only the term with 1 plugged in for n, right, which is 9/10, or if you want to put that as a decimal, 0.9. Right, what is S2? Well, it's the first two terms, so 10 to the negative 2, sorry, 10 to the negative 1 plus 9 times 10 to the negative 2, right? But that's 9/10 plus 9 over 10 squared, which would be 100, right? Or 0.9 plus 0.09, right? 9/10 plus 9/100, which gives me 0.99. All right, so then S5, what would that have to be? All right, well, it would be the first term plus the second term. And I think you can probably tell the pattern we've got going on here. It would be plus the third term would be 0.009 plus the fourth term 0.0009 plus the fifth term. So that's going to be 0.99999. All right, so we have these partial sums. So in other words, the first term is 0.9. If you add in the second term, you get 0.99. If you add in the third, fourth, and fifth terms, you're up to 0.99999. Right? So if we look at this, it certainly seems like this sequence is headed towards something, right? So does this sequence converge? Is our question here? Well, it certainly seems to converge to 1. So we'll say it looks like the limit as n goes to infinity of Sn is equal to 1. Okay? So in part C, based on your answer to part B about the sequence converging or not, is this series convergent and divergent, right? Well, if the sequence converges, then the series converges. If the sequence of partial sums converges, I should say, then its series converges, right? And it converges to that same value, right, that the sequence converged to. So what we would say here is that the sum from 1 to infinity of 9 times 10 to the negative n would equal 1. Now, just kind of a fun side note here, you know, what's another way of stating this, right? You're continuing to add 9s forever and ever, right? So one way to say this would be that n equals 1 to infinity, 9 times 10 to the negative n, should equal 0.999 ... on and on forever, right? But we know how to write that. That's 0.9 with a bar over it, right? So what does that tell us? That tells us that this infinite decimal representation is, in fact, the same as the number 1. Kind of a fun side note there. All right, now the problem that we just did was an example of what's called a geometric series. It was expressed a little bit differently than you're going to see in this definition, but it can be made to look just like it. But a geometric series is one in which we have this form. We're summing infinitely. We have a constant factor, and then we have the base of an exponent raised to the power n minus 1, right? So it's going to always look like a plus a times r plus a times r squared, and so on and so forth. This geometric series is going to come up a lot, so we're going to make a very general statement about it. This series is convergent when r is less than 1, when the absolute value of r is less than 1. Okay, and that makes sense because when r is less than 1, we know that when we raise it to a power, right, and we had this discussion before, right, if you raise, something like 0.8 to the power of 2, we know that it actually gets smaller, right? And so your terms are going to have, your terms are going to be smaller and smaller and smaller as you go, so it makes sense that it might actually settle down on a number rather than just go off to infinity. It turns out that we know exactly what that sum looks like. Okay, so anytime you have a geometric series, the sum is a, right, the constant part, divided by 1 minus r. And in fact, that previous example that we did was a geometric series. It was just kind of in disguise, I suppose. So when we had, what did we have? It was 9 times 10 to the negative n. You might say, well, okay, 10 is not less than 1. Well, no, it's not, right? But notice that the n up here is positive, and so what I could do here is say 9 times, this would be 10 to the negative 1 raised to the positive n, which would be 9 times 1/10 to the n, right? So that would have ended up being our r value. Right, but at any rate, okay, how do we know that this is the sum? It's kind of strange to be able to say this is always going to be the sum. So the proof of it's kind of a cool one, and it uses the idea of partial sums. So let's do the partial sum s sub n. So the partial sum s sub n, we know would look something like this, right? Our first term would be a, where, and remember why is that? When you plug 1 in for n, you put 1 minus 1, so it's r to the 0, and r to the 0 is always 1, right? So a plus, when n is 1, ar plus ar squared, right, plus dot, 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 and then I'm going to write 2 more terms for the very end, a, or just 1 more term for the very end, I guess, a times r to the n minus 1. So that would be the last one when you're literally plugging n in that spot. All right, and then what we're going to do is we're going to take this equation and we're going to multiply every term by r, both sides by r. So if I take r times s sub n, then what we're going to do is multiply r by ar, by ar squared, and so on. So what's going to happen though is I want to line these up, so I'm going to put the ar right here plus the ar squared right here plus ar to the n minus 1. But of course, when we multiply this last term by r, right, r times ar to the n minus 1, that's going to equal a times r to the n minus 1 plus 1, right, which is just a r to the n. So it's going to give us one more term. And so what we're going to do here is we're going to subtract these two equations from one another. So if I subtract them, I get Sn minus Rsn. And of course, what's going to happen here is all these terms are going away, right? Because they have a match and we're subtracting them. The ones that don't have a match are the very first and the very last. All right, so we have that. Now what we can do is do some factoring. So I can factor out S sub n from the left side, and I can factor out 1 minus r sub n, factor out a from the right side to get 1 minus r sub n, right? And then I'm able to isolate this. So what this does is it gives me a formula for the nth partial sum. So S sub n is always going to be equal to a 1 minus r to the n over 1 minus r. So if I take the limit as n goes to infinity of a times 1 minus r to the n divided by 1 minus r, let's think about what happens as n gets really big. as n gets really big, what happens to r to the n? Well, it goes to 0, right? Since r, the absolute value of r, is less than 1. So that means that this goes to 0, and so what are we left with? We're just left with the a times 1 on top, 1 minus r. So that's a pretty understandable little proof of why it is that this series, in fact, converges to that particular number. It sums to that particular number. All right, so we're going to do a couple examples here that actually work with geometric series, and I'll try to show you some of the tricks you got to do in order to successfully figure out what their sum is, right? So let's just over here, let's remind ourselves of what we know. We know that if it looks like this, then it will converge to this as long as r is smaller than 1. The absolute value is smaller than 1. So here's the deal. When you get something like this series, your whole goal is to make it look like what's over there on the left. Okay? So in other words, you need to figure out what a should be. You need to figure out what r should be. So if you're going to figure out r, what you need to do is figure out a number that if you raise it to successively higher integer powers or whole number powers as you go along, you get the next term in the series. So let's first, when you have these fractions, it's usually nice to kind of take it one at a time, look at the top and then look at the bottom. So the first question to ask yourself is, can I get from 2 to 6 and then from 6 up to 18 by raising something to a power? In other words, 2 to what power equals 6, right? 6 to what power equals 18? The answer there is nothing really, right? Nothing nice. And so what we want to do in a case like that is say, okay, I'm not really happy with the numbers I see. It's not obvious to me that 2 to something is going to give me 6. 6 to something is going to give me 18. So is there something that I can factor out of these numbers? And we can see that they all do have a factor of 2, right? So my first step would be to say, let's rewrite it so it's 2 times 1 over 5 plus 2 times 3 over 25 plus 2 times 9 over 125. And now, ignoring the 2, let's ask ourselves the same question about 1 to 3 and 3 to 9. Okay? Can I write those as something to a power and get each next term? And the answer there is yes, right? So if I think of the base as being 3, then 1 can become 3 to the 0. 3 can be 3 to the 1. And 9 can be 3 squared. So you see the game we're playing here? We're trying to separate out what can be raised to a power and what should be the constant, right? So at this point, 2 has got to be a part, at least, of what our a is going to end up being. All right, so now let's turn our attention to the bottom. We have 5, 25, and 125. Well, that's actually great news because I can think of this as 5 to the 1 because I know 25 is 5 to the second, right? And 125 is 5 to the third. So it looks like I've already got those in a position where they can be a particular value as the base raised to different powers. So that's really good. But again, let's remember what we're looking for. We're looking for an r value, right? a single R value, right? So not an R value on top and an R value on a different one on bottom. We want a single R value all raised to powers. So what I want to be able to do is think of, right, A times R to the n minus 1. So I need to take this stuff that's raised to these powers and collapse it down into just a single R value. And right now, what's preventing me from doing that is these exponents are not the same, right? The ones on bottom are all one more than the ones on top. So one thing that we can always do is take out whatever's necessary from this. In this case, we'll do these powers that are higher so that the exponent drops down to match the one on top. So here's what I mean. 5 to the 1 could be written as 5 times 5 to the 0. Agreed? Because, of course, 5 to the 0 is just 1. So 5 squared can be written as 5 times 5 to the 1. And you might think that's kind of funny the way I'm writing that, but of course what I'm trying to do is make the powers on top and bottom match perfectly, right? So then 5 to the third could be 5 times 5 squared. So here's what we've got. We have now 5 is going to be a part of my A value, right? It's going to be part of the constant. So now you can see this taking shape, right? This first term is going to be 2/5 times 3/5 to the 0 plus 2/5 times 3/5 to the first plus, oops, didn't really want to put that. Erase that real quick. So plus 2/5 times 3/5 squared, and so on. All right, so now we've got it. We can now see this is my A, right? 2/5 is the A, so this is going to be the sum from n equals 1 to infinity of A, which is 2/5, times 3/5 to the n minus 1, right? So there's our R, and there's our A. Once we have it in this form, now we're able to easily write out what the sum is equal to, right? So rewriting this over here. So A is 2/5, right? So I'm just copying just directly from this formula. 1 minus 3/5. And so, of course, that's pretty convenient. 1 minus 3/5 is 2/5. So this means this thing sums to 1. All right. Now, one little side note here that I actually meant to say about infinite series, geometric series specifically before, but I'll comment on it right now, is that this is the form that allows you to write the sum like this, right? However, you will also see it written like this: n equals 0 to infinity of AR to the n. Notice the result is the same, right? Here, if you start with 1, if you put 1 in this formula, you end up with R to the 0 as the first term. Here, if n equals 0, you put a 0 there as the first term. So either one of those are acceptable. So this is the way that the book writes it. But if you end up writing it like this or seeing it like that, then this also is able to be written. You can also write the sum as A over 1 minus R directly from this as well. All right, so a couple of theorems that we want to make sure that we are conversant in here um, that do what you would hope is true, I guess, but it's just formalizing it and giving us permission. So if you have a constant inside, you can always pull it out, right? So in other words, that a in the geometric series could be pulled out of everything. So in other words, in that last example, right, when we ended up with 2/5 times 3/5 to the n minus 1, it would be perfectly acceptable to pull the 2/5 outside of the summation and write it like this. So that's totally fine, just factoring out a 2/5 essentially from every term. So you can factor out. If you have two series that are both convergent, then what you can do is if you have two different terms being added within the series, you can separate them into two separate series, and the same thing with subtraction. Okay, so we're going to see, I think it's number 3, the subtraction one, in play here. All right, so we want to ask the question, is this series convergent or divergent? And if it's convergent, let's find the sum. All right, so knowing that I can separate out our separate a complicated formula into two series when I have subtraction or addition, what I'm going to start by doing is just taking this thing and breaking it up as two separate fractions. So 4 times 5 to the n over 6 to the n minus 1 minus 5 times 4 to the n, 6 to the n minus 1, right? So that, of course, is these, of course, are the same. But remember what we're shooting for again. Let me just sketch it over here. We're searching for n equals 1 to infinity of a r to the n minus 1, right? So if we can make it look like that, then we know what it sums to. All right, so just like we did before, what we'd like to be able to do is take these exponentials that are on top and bottom and combine them into just a single base. And right now we don't have the same exponent on top and bottom, so let's work on doing that. Since n minus 1 is the way we want it expressed, I'm going to say we're good on the bottom. We like what I see down here. It's the top that I would like to write as n minus 1. But I can definitely do that, right, if I take a single 5 away from this 5 to the n, right? I just remove one of them and stick it over here as a 5 to the 1. And I can do something similar over here. Right? And then this allows me to easily see what my a's are and what my right? If I have 5 to the n minus 1 over 6 to the n minus 1, that can become 5/6 to the n minus 1. And then same thing here, 4/6 to the n minus 1. And then lastly, we know what to do with a single series that looks like this, not multiple terms, but from the previous page, right, we were given permission to break our series apart. So we'll do that. So this will be n equals 1 to infinity of 20, 5/6, n minus 1, minus a separate series. And let's go ahead and make 4/6 into a reduced fraction, 2/3, right, minus that. So we know that this A is 20, R is 5, 6, and then 20 over 1 minus 2/3. All right, so on bottom we have 6, 6 minus 5, 6 is 1/6. And here I have 1 minus 2/3, so that's 3/3 minus 2/3 is 1/3. And then multiplying by the reciprocal, I get 20 times 6 over 1 minus 20 times 3 over 1. So it looks like 120 minus 60. So after all that work, we get that this ugly thing just sums to the number 60. All right, let's talk about a couple of other types of interesting series that you'll see. So this one here is what we refer to as a telescoping sum. Okay, so our instructions here is to show the series in fact is convergent. And they want us to do this by expressing the series as a sequence of partial sums, right? Remember what that means, that S sub n sequence of partial sums as a telescoping sum, okay? By writing the series in this form, okay? And at first you might not understand what they're exactly asking us to do here, but we'll get to that. But let me just say this for a moment. I want you to think about, you know, the old style telescope that like a, you know, like a captain of a ship would use, right? So you have your telescope that's got, kind of gets successively thicker, right? At the very least, maybe you've seen this in cartoons or whatever, right? So the old style telescope that goes like this, and then what's the captain of the ship able to do? Able to put it, you know, collapse it down so that you only see, right, basically the first one and the last one. They collapse it down just like that, and you can stick it in your pocket, right? So I think that to me is what I always envision when I envision a telescoping sum. And so that's kind of the principle, that when you have a telescoping sum, it turns out that the kind of the first and the last end up being important. But you'll see how that works in a moment. So first, what's this, right? What are we talking about here? We're taking this and writing it this way. I hope that this at least looks a little bit familiar to you. The place you would have done this is something that looks very similar to this whole idea of adding up, right? You may have done something like this when you were asked maybe to do a problem like this, right? And the idea was, can it be written as a over x plus 4 and b over x plus 5, right? So remember this idea of a technique of integration by breaking things into partial fractions. So that's exactly what we're going to do here, right? So remember, the idea is when you have something like this, a couple of binomials factored on the bottom of a fraction, you know that it could have come from two different fractions being added together that have this form. So, and so, you know, how do you know that, right? Because you get a common denominator, right, between these two, and you add these together, and that could produce something like this. So here's what we're going to do. We're going to say this should equal something like this, but I don't know what A and B are supposed to be quite yet. All right. Now, the technique here for figuring out what A and B are is understanding that we have a valid equation that we're staring at right now. So we just, on both sides, multiply everything by n plus 4 times n plus 5, n plus 4 times n plus 5, n plus 4 times n plus 5. Okay, and so of course we get all that wonderful cancellation over there, right? We get that, and we get that. So what happens here switch my colors, is we get 1 equals a times n plus 5 plus b times n plus 4. So a n plus 5a plus bn plus 4b. And what I can actually do here is think of it like this. This 1, there is no n term over here, right? So I'm going to say this, 0n plus 1 is going to equal, I'm going to put the two n terms together. So an plus bn would be a plus b times n. And then plus 5a plus 4b. So what I've done is I've separated it into the n terms and the constant terms. What that allows me to do is say, well, then that means a plus b must be 0. And it means that 5a plus 4b must be 1. So 0 equals a plus b, and 1 must equal 5a plus 4b. So if a plus b equals 0, that means a equals negative b, right? And so then that means down here I can make a substitution. So this will be 1 equals 5 times negative b plus 4b, which is negative 5 plus 4. So that'll be 1 equals negative b, so that means b equals negative 1, right? And so therefore, because of this, a must equal 1. So what that means is that this sum here (1 over n plus 4 times n plus 5) can be written as 1 over n plus 4, and then since b is negative 1, let's say minus 1 over n plus 5. This is a valid way to rewrite this expression. Okay, so how is that helpful? So the reason that that's helpful is now we're going to start writing out our partial sums, okay? So let's just write out what S sub n would have to look like, right? So remember what S sub n is. S sub n is us sticking a number n up here, okay? So S sub n, we're just going to start with 1. So plugging 1 in here would be 1 over 5 minus 1 over 6, right? So this would be, because remember, I know it's kind of confusing to use n in two different places, but what is this? This is I equals 1 to n of 1 over I plus 4 minus 1 over I plus 5, right? So this is I equals 1 plus, when you put a 2 in here, right, you put a 2 in for I, you get 1/6 minus 1/7 when I equals 2, plus 1/7 minus 1/8 when I equals 3, plus dot dot dot, and then of course when we let I equal n, that's when we get 1 over n plus 4 minus 1 over n plus 5. Now hopefully you can kind of see the telescoping that we're talking about here. Okay, so whenever we do this, what's going to happen? Well, this minus 1/6 and this plus 1/6 would zero out. This minus 1/7 and this plus 1/7 would zero out. This minus 1/8 and then the one that came next that I didn't write would zero out. And then the one that came right before us, this would have been minus 1 over n plus 4 would cancel out with the positive 1 over n plus 4. And so after all of that, let's think about what we're left with here, right? We're left with the partial sum is just simply 1/5 minus 1 over n plus 5. All right. Now, we can take the limit of that, right? And we know the limit of the sequence of partial sums is the same as the sum of the series. And if you let n get really big here, this thing zeroes out, and so you're left with just 1/5. So this series we know sums to a fifth. So hopefully you can kind of see the telescoping action here, right? Like all these guys in the middle collapse down, and all you really see is the first and the last, right? That's that action that's happening here in this partial sum. So kind of a cool example there. All right, now we've done a lot of series here where we end up with a convergent series, okay? But what about divergent? We haven't even done an example yet. All right, so let's think about this one for a second. Let's just go ahead and plug in a couple of terms, right? So if n equals 1, then we have 4 on top and 7 on bottom, right? When n equals 1. When n equals 2, we have 7 on top, 12 on bottom. When n equals 3, we have 10 on top, 17 on bottom. Okay, and then how about just for fun, let's do 100. Let's see what happens there. So then I've got 301 on top and 502 on bottom. So what we notice here is that we started off above a half. We're still above a half. We're still above a half. We're still above a half, right? So it doesn't, in fact, this is getting a little bit bigger even as I go. So the fact that my terms are actually getting bigger as I go along means I'm certainly not expecting this thing to sum to any finite number. This should, because it just kind of keeps growing, should be divergent. It should sum to infinity, right? So I'm thinking this is divergent, right? So, oh, and I guess I said so, right? So, okay, I could always use that too. But definitely thinking divergence here. So how do I show that? Okay. Well, one thing we can always do is look at just what's in here. So forget about the sum for a second. What happens in the long run, right? As we kind of are sketching out here informally, but formally, what happens in the long run as I let n get huge, right? Remember what we do with things like this, we did this in the last section, is, right, we take 1 over n so that we get just a constant on the bottom, multiply by 1 over n on the top and the bottom to make it legal. So we end up with 3 plus 1 over n, 5 plus 2 over n, and we know that these guys both go to 0 as n goes to infinity, so this should be 3/5. Well, if the members of the sequence are settling down to 3/5, then if you're adding those members of the sequence to themselves over and over and over again, then there's going to be no limit to what that sum can go to. So the way we would say this is the series is divergent because its terms do not converge to 0. All right. So I'm going to go a little out of order here. So this one that that problem we just did, here's the formal thing to give us permission to say this. The test for divergence. It says if the limit of the terms in the series does not exist, or if it is not 0, then the series is divergent. And that's exactly what we said right here. Okay, so if that ever happens, you have to have a divergent series. Okay. So let me back up here now. So the one in example 4 converge, and it was also true that these converge to 0. So what it says is, if this theorem says if the series is convergent, then you know that the members or the terms have to converge to 0. Okay. So we got to be really careful about the direction here. So if you already know the series is convergent, then it must be that the terms go to 0. This one's saying if the terms don't go to 0 or don't exist, then the series is divergent. Okay, but we do have to be very careful here. Just because the terms of a series go to 0 does not mean the series has to converge. So let me give you the classic example, and I'm not going to go through it, but there's a good write-up of it in the book. So I really encourage you to go look at example 7 in the book. But this series right here diverges. Oops, that's supposed to be a G. Diverges. So the series 1 plus a half plus a third plus a fourth, even though the terms are getting smaller and smaller and smaller and heading towards 0, it actually is a divergent series. It does not sum to a finite number. So again, I'll let you look at the text to really kind of flush out why that is. And we'll come back to this example later. But for now, just want you to take one. I think that our intuition would tell us that this would converge since they're getting smaller and smaller. It turns out they don't get small fast enough is kind of the way to put it. So that diverges. So don't fall into the trap of saying, oh, the terms go to 0, so the series, when I sum them up, automatically converges. That is not always going to be the case. All right, so our last example here, what I want to do is take this idea of a repeating decimal, 3.612, right, where the 612 repeats itself over and over, and write it as a fraction. Okay, so when you learn about repeating decimals, whenever it is that you learn that kind of thing, 2/3, right? You figure out what that is. You figure out that that's 0.6 with a bar, right? Because you say 2 divided by 3, 3 goes into 2 0 times, right? 3 goes into 20 those 6 times. 6 times, and you realize, oh, it's just going to repeat forever and ever, and so then to put the little bar over it. But how do you go the other way? How do you take a repeating decimal and figure out what its fraction is? And the answer to that is infinite series. All right, so here's what we're going to do. We're going to take 3.612 and we're going to write it out, okay? So that's 3.612, 612, 612, and I'll stop there, okay? So we get the idea. All right, so what does this mean? Well, it's 3 plus 612, and then this is the tenths, hundredths, thousandths place, right? That 2 is in the thousandths. So it's 612 over 1,000. Plus, well, we got another 612, right? But where's that? 2 right there. That is in the millionths place, right? So And you can see the pattern here, right? This one's going to be in the billionths place, so it's 612 billion. All right, and that's quite enough of that. I think that's enough to get the pattern down. All right, now if we're looking at this carefully, and I think back for a little bit, I think to our first page. There we go. Yeah, right here. Right? We had this business of 10 to the negative 1, 10 to the negative 2, which was really 9 divided by 10, 9 divided by 100. So it's kind of reminding me of that. Remember, we made the comment that this really was a geometric series, right? And we know with geometric series that they sum to this if we can get them in the right form. So what I'm going to try to do here is put this in the proper geometric series form. All right, so here we go. So this will be 3 plus, well, if I'm going to put that in the proper series form, I think I want exponents to start appearing. So let's do 612 over 1,000 would be 10 to the third. A million would be 10 to the sixth. And then a billion would be 10 to the ninth, and so on. All right. All right, so now the 3 here, it's hard to see how that 3 really fits in, so I'm just going to keep it off by itself, right? But this is the part that I think can definitely be an infinite series. All right, so here's what we're going to do. We're going to start to write this as a summation, okay? So I'm going to try to get this in summation form. So this will be n equals 1 to infinity. The 612 isn't really doing anything. It's just kind of hanging out, right? So I'm kind of thinking that's going to be at least part of what my A is, right? And let's just go ahead and write over here what we're shooting for, right? This is AR to the n minus 1. That's what we're going for, because if I can say that, then I can do this, right? So 612 over, all right, now I want my first term to be 10 to the third. I want my second term to be 10 to the sixth. I want my third term to be 10 to the ninth, right? So what I'm really doing here, aren't I, is I'm saying whatever n is, I want to multiply by 3, correct? So this is 10 to the 3n. Okay, so that's good, I guess. So 3 plus, now look over here. Not only do we have n minus 1, but we don't have a 3 to the n, right? So what I'm going to do is use my exponent laws, and I want to make it as something just raised to the nth power, right? And so just raised to the nth power would be 10 to the third in here. Okay, so let me start to run out of room here. So this would be 3 plus the sum from n equals 1 to infinity of 612 over 1,000 to the nth power. Okay, so things are kind of starting to take shape here, I guess, right? Okay, so 3 plus n equals 1 to infinity of 612 times 1 over 1,000 to the n. So we're getting really close here, okay? I think that we can look at this and say, I've got my r, right? I've definitely got my r. And it looks like I have an a, but there's still one problem. I need it as n minus 1, not as n. Okay, but we've played this game once already, right? What I can do is I can make this be n minus 1, right? But where did that extra 1 go? Well, I've pulled it out, right? So 1 over 1,000 to the first times 1 over 1,000 to the n minus 1, those put together will equal 1 over 1,000 to the n. So now I've gotten it to n minus 1 legally. And so we're just about there. This will be 3 plus n equals 1 to infinity of 612 over 1,000 times 1 over 1,000 to the n minus 1. That's my A, that's my R. So this becomes 3 plus 612 over 1,000 over 1 minus 1 over 1,000, which, after a little bit of, I'm running out of room here, so this will be 612, and this will be 999 over 1,000. The thousands cancel, so it'll be 999. And so after getting common denominators, I apologize for running out of room, but I'll leave the rest of the fraction work to you. I get this awful number, or beautiful number, depending on your perspective, of 3,609 over 999. That is the fraction representation of the infinite repeating decimal 3.612 with a bar over it.